We're going to continue with the back page of the Related Rates Notes 2. We just got through talking about similar triangles and shadow problem. Here's another similar triangle problem, number 3. A conical tank, vertex down, so this is the shape we're dealing with here, 40 feet across, so from one end to the other is 40 feet, and 40 feet deep. From the top to the bottom, the vertex is 40 feet deep. If water is leaking out of the tank at 80 cubic feet per minute, find the rate of change of the radius of the water when the water is 8 feet deep. So here's the volume formula that we're going to be working with related rates here. Volume of a cone, 1/3 pi r squared h. Let's go ahead and try and list out as much information as we can based off of what the problem gives us. So, and we also know this may be a similar triangle problem, so we're going to make that adjustment as well. So 40 feet across the top and 40 feet down. If we just look at a two-dimensional version of this cone where we split this in half and just look at a two-dimensional version, we're going to come across a right triangle. Okay? So if we just take this portion and we just focus on this portion, this right triangle portion of the cone. Okay, so I'm going to draw a simpler diagram here showing the top of the tank, water level of the tank at any given moment, the height of the tank, and then the height of the water level at any given moment. So this is the diagrams given here. The tank is 40 feet across, so that's a diameter. So 40 feet diameter means 20 feet radius, and the height is going to be as given here, 40 feet deep. All right, so water is leaking out, so we know that the rate of the volume changing is going to be negative because the volume is going to be decreasing over time. So if that's the case, then we want to have a negative associated with that dV dt. Another way to tell that this is talking about dV dt is looking at the unit of measure. Unit of measure tells us is cubic feet per minute. Cubic feet is volume, per minute is a rate, so cubic feet per minute is going to be volume rate of change. So volume's rate of change will be dV dt. So dV dt is negative 80 cubic feet per minute. Find the rate of change of the radius. So we know radius is r, but we're asked to find the rate of change of the radius. So we're looking for dr dt. Okay, so dr dt is what we're looking for when the water is 8 feet deep. So when the water is 8 feet deep, so we're going to say h is equal to 8 feet. Now, we want to put a star next to this h equals 8 feet because we don't want to put this value into the equation too soon. Okay, so we're going to come back to this, but this is not going to be used at the beginning portion of our problem. Now, if we look at what we have here, we're trying to find dr dt. We're given dV dt, but we don't have enough information about dr dt. So right now, if we were to find the derivative, which we can, there's two variables here, r and h, that are related to each other by multiplication. We'll have to go through product rule. If we go through product rule, we're going to get dr dt, we're going to get dh dt, and dV dt. And so right now, we're missing dr dt and we're missing dh dt. So the issue is there are too many variables. We want to try and condense this equation to have less variables. So if we can find a way to relate radius in terms of height or height in terms of radius, then we can substitute one variable in terms of the other, and that will make our equation easier to work with, thereby making it easier for us to solve our problem. So the way that we're going to relate radius and height is using similar triangles. So much like the shadow problem, we can say small radius. So radius of in this case, this is the radius of the water level. Small radius is to the big radius, so r over 20, as small height, which is height of the water level, over the height of the entire container. So h over 40. So small radius is the big radius as small height is the big height. Now we have radius and height related to one another using proportions. Now if we multiply, cross product here, we get 20h is equal to 40r. We can solve for h. H is equal to 40 divided by 20 is r, so h is equal to 2r. So we have, this is now our formula that will relate height and radius. Now if we look at our equation here, or if we look at what's given and what's the problem is asking for, the problem is asking for dr dt. So that gives us a hint as to how we want the equation to look. If we can rewrite this equation in terms of just v and r, meaning just volume and radius, then when we find the derivative involving radius, then we're going to have dr dt, and then we can use that to help us solve for what we need, which is dr dt. Okay, so we're trying to get our equation in terms of r, which means we want to replace h in terms of r. So if we want to replace h in terms of r, we can say h is equal to 2r. So now every time we see h, we can replace it with 2r, since using similar triangles, we've shown the relation between those two variables. All right, so going back to the volume equation for a cone, pi volume is equal to pi over 3 r squared h. We're going to replace h in terms of radius, so h becomes 2r. Now if we clean this up just a tad bit more, pi over 3 r cubed times 2, right? This r squared times r is r cubed. The 2 I'm going to pull in front, let it share the coefficient with the pi over 3. So now we have a much simpler equation to work from, eliminating the height because we've replaced height in terms of radius. Volume is equal to 2 pi over 3 r cubed. Now, some of us may try and find the derivative at this point. If we do that, you can, but you want to try and simplify, especially if you have two variables that can combine with one another. Students in the past have tried to go through product rule involving r squared and 2r, and that's unnecessary because we can combine this, which we can just apply power rule. There's no need for product rule here. All right, so we have volume is equal to 2 pi over 3 r cubed. We can go through power rule here, since remember 2 pi over 3 is just a coefficient. Pi is just a number. These are not two variables. The only variable here is r, and then the 2 pi over 3 is just a number that happens to be in front of r. So we'll treat 2 pi over 3 as simply a coefficient in front of the r variable. All right, so now let's find the derivative. V becomes dv dt. R cubed becomes 3r squared, so r cubed becomes 3r squared, so the 3 comes down, r squared, and then dr dt. All right, we found the derivative of r, and then we have to attach a dr dt. And the 2 pi over 3 is just going to hang out here in front. It's just a coefficient. Now, we found the derivative, okay, with respect to time for both variable v and for r. Now we can start plugging in. We know what dv dt is. Negative 80, that's what's given to us in the beginning. We know what radius, well, actually we don't know what radius is, so we'll leave that blank. But we do know what dr dt is, or dr dt is what we're looking for. So we actually have another missing variable here. How do we find radius then? Because it's not given to us. Well, we do have something that relates height and radius. So we know at this moment in time, the height is 8 feet. So if I plug 8 in for h, then I can solve for r. 8 divided by 2 is simply going to be 4. So at this moment in time, the height is h. And we also know at this moment in time, the radius must be 4, because we have this relationship that will convert from one form to the other. So we can replace our radius, r, with 4. So we should have everything now. We have dv dt, which is negative 80. We have r, which is 4. And now the only missing variable is dr dt. So then we can just solve for the missing variable dr dt. 2 times 4 squared is 16. 16 pi is 4 squared, times 2 is 32. Divide both sides by 32 pi. So negative 80 divided by 32 pi reduces to be negative 5 over 2 pi. And we have our answer here. Unit of measure is feet per minute. Okay, number 4 here. This is a cylinder problem. A coffee pot has the shape of a cylinder with a radius of 5 inches as shown in the figure. Let h be the depth of the coffee in the pot measured in inches, where h is the function of time. The volume V of coffee is given by the rate of -5 pi square root of h cubic inches per second. And the volume of a cylinder is given to us, V is equal to pi r squared h. Find dH dt. All right, let's list out information that's given to us. We know what the volume equation is, V is equal to pi r squared h. The rate at which the volume is changing, so we know dV dt must be this value that's given to us in the problem. So dV dt is -5 pi root h. Okay. We know the radius is 5 inches. Okay. And then we know the volume formula is V is equal to pi r squared h. Okay. Now this looks like the cone formula in the sense that there's a volume, there's radius, and there's height. But the difference here is that if we look at a cone, if we kind of think about water level changing inside a cone, that radius is always going to be changing depending on where you are, where the water level is in that cone, right? If it's down here, the radius will be really small, but if it's up here, the radius will be a lot larger. But if we think about a cylinder here, it doesn't matter where the water level is. The radius is going to hold on to a constant 5 inches. Okay? It's not shaped like a V, like this diagram, so we know the radius is going to remain constant, which means that if we know what the radius is in the problem, we can just replace that with whatever the constant is, because it's never going to change. So we don't have to keep that variable, since that variable ends up being a constant in this problem. So we can just replace radius as the value in the problem. So our updated equation is now going to be volume of the cylinder will be pi r squared h, pi 5 squared h. 5 squared is 25, so V is equal to 25 pi h. Okay, so this is a lot simpler because we don't have to go through similar triangles. Now we're down to 2 variables, and we can just find the derivative and find the missing information, which is dH dt. We're looking for dH dt here. All right, so let's find the derivative with respect to time for both these variables. So V becomes dV dt. 25 pi h, remember 25 pi is just a coefficient. Really, the variable that we're trying to find the derivative for is h. So the derivative for h is just 1, but we have to attach a dH dt. So let's see what we can do. dV dt, we have a value for that given to us in the problem, -5 pi root h. So replace dV dt with -5 pi root h. Solve for dH dt, we'll divide both sides by 25 pi. And look, the pi will cancel out. The 5 and 25 will reduce to be -1/5. And because we don't know what the value of h is, we're going to have to represent dH dt as a function of h. So that tells us that it's okay for our answer to have h in it because it wasn't given to us in the problem. So dH dt is simply going to be -√h over 5 inches per second. And again, we know that these are negative values because we're told that the pot is changing at a rate of 5 pi root h. So that's negative, indicates that the coffee pot, the volume is going to be decreasing. It's going to be falling. So dH dt is -√h over 5. Unit of measure is inches per second.